Good afternoon. Welcome to KAUST Live. We're coming to you from the Winter Enrichment Program on KAUST campus. This year's theme is Human-Machine Future, which aims to explore the ever-changing role that technology plays in our daily lives. Here with us today to talk about that is Carolyn Porco. She is a planetary scientist, and she's perhaps best known for her work on the Cassini mission in Saturn. Carolyn, thank you so much for joining us today.
Thank you for having me.
Yeah. So I want to break our conversation into a couple of parts. You have a keynote tonight at 5:30, which is going to be also streamed on Facebook, so I don't want to tread on that too much. But I did want to ask a few general questions for context. And I thought maybe we could actually get into some of this human-machine future and talk a little bit about how space exploration, particularly as scientists send these crafts out to the outer reaches of the solar system, is entirely machine-mediated for the moment. So talk to us a little bit about Cassini, why Saturn was chosen, and how you got involved in that mission.
Okay, so that whole thing begins with, well, it begins at the beginning. It begins with the formation of NASA in 1958. And the charter of NASA was to conduct a survey or understand the solar system and to conduct the program in three parts. First part called for reconnaissance missions. You just quickly send a spacecraft outfitted with proper scientific equipment, send it by a planetary body, one of the planets, and gather up as much information as you can. Okay, the term, of course, comes from the military. NASA was an outgrowth of NACA, which was the National something on let's see, I can't even remember what it stands for now. Sure. Committee on Aeronautics. It's just a committee, and it became an agency. The second part of the exploration of the solar system was going to be orbiters. Once you've done the reconnaissance, you put a spacecraft in orbit around a body, and of course that allows you the leisure of examining things in depth and understanding it in all its parts and how all those parts interact. And then finally, where it was appropriate, it was thought back in 1958 that the third step would be sample return. You would grab a sample from the surface of a body that you could actually land on and grab a sample from. You might even return a sample of the atmosphere of a body that maybe didn't have a surface. So that whole scheme was there right from the beginning. So we had lots of missions that were reconnaissance missions. The initial Mariner missions to Mars and to Venus were reconnaissance missions. And the most famous, the greatest actual mission that was ever, a reconnaissance mission that was ever done was Voyager, and that was the grand tour of the outer solar system, and it hit Jupiter, Saturn, Uranus, and Neptune. So once we did that, it was just an obvious no-brainer that the next thing you would do is put an orbiter around those bodies. And in fact, after Jupiter flyby in 1979, Voyager Jupiter flyby, plans started to be made to put an orbiter around Jupiter, and that orbiter became Galileo, the Galileo mission. And then, of course, after Saturn encounter, it was just obvious that we needed to go back. There were so many fascinating things about the Saturn system we wanted to know more about, and so that mission became Cassini. And it was from the outset meant to be an international mission and involved the European Space Agency.
And so your involvement started with Voyager 2, am I right about that?
I was, yes. In fact, I was at Caltech, the California Institute of Technology, which runs JPL, the Jet Propulsion Laboratory. I was there as a graduate student when Voyager went by Saturn, and there was a person there in our department, which was the Department of Planetary Sciences, and he was on the Voyager imaging team, and there was so much information, there was so much data, images, and spectral information, and just people were drowning in it. It was just, they couldn't cope. The teams were, there was so much to do, and so the graduate students who were associated with those team members, got to do amazing things with things that had never been seen before, information that had never been collected before. So 2 very nice topics fell in my lap to work on for my doctoral dissertation. One of them was the spokes that were seen in Saturn's rings, and another was these eccentric rings, narrow eccentric rings that were embedded in the main rings of Saturn. And so I did that. I did my doctoral dissertation on those 2 topics, and it so turned out that the eccentric ringlets that I was studying in the rings of Saturn are the Saturnian equivalent of the rings that had just been found around Uranus in 1977 from the ground, from ground-based astronomical observatories. So the imaging team leader, as he did at every flyby, in anticipation of the flyby, he added people to the team who had the proper expertise. Because when those teams were first put together, I mean, we knew nothing about the solar system, about the outer solar system. So he had to shore up his team with the proper expertise and knowledge. And so when we're on approach to Uranus, and he's looking around to see who can we get who knows something about Uranus, in particular the Uranian rings, well, there I was. And so I was added to the Voyager imaging team. And that basically was how this all got started. I was there for Uranus, I was there for Neptune. By the time we got to Neptune, I was leading the small group of people on the team who were interested in rings. And then right after Voyager was over, there was an announcement of opportunity. We're going to start the next mission back to Saturn. And I applied to be the imaging team leader, and I got it, and the rest is history.
How do you plan? I mean, that's such a big thing to think that you have to do all the planning, and then you launch this, and it travels for near a decade before it even reaches, and you start your work. I mean, how do you do all of that? Give us at least some little bits of an idea.
You have to get your head around something which even I have a hard time getting my head around. The Cassini mission was ongoing for 27 years. 27 years. That's over a quarter of a century. And we didn't do all the things that needed to be planned before we got into orbit. We didn't do that before launch, but of course, obviously, we designed the spacecraft. The engineers at JPL worried about that, but the scientists had to add their, we were involved just in case they did something that, prevented us from taking important observations. It was critical that we were involved in that. We were involved in, of course, the design and the build of all our individual instruments, and in our case it was the cameras. My science team oversaw the development of the cameras and worked with the engineers to make sure that the cameras were going to suit our scientific needs. And then we were planning what the mission design would be, how many flybys of this satellite, how many orbits would we be inclined to the ring plane so we could look down, and so on. And I don't even think we settled completely on which mission we were going to fly by the time we launched. And then along the way, the 7 years it took us to get there, we are literally planning every 30 seconds of a 4-year tour. I mean, that's what it takes. And it was lots of telephone calls, teleconference calls, lots of arguing, and I mean, and on it goes. And in our case, I had to build the operations center. We had to build the databases that would collect all the information that we'd gather, the images. We'd have to derive, as soon as they hit the ground, basic information about the images called metadata, so that when my team members wanted to do something scientific, as soon as the data hit the ground, they had the information there available to them. We had to build the software that helped us figure out, how to choose images and how to set the camera parameters so that we took the right image. And then that was what we call the uplink part of things. The downlink part of things is when the images hit the ground, like I said, they get ingested into the database. And I guess I described part of that already, but there was another part of our job that no one else had really, and that was to process the images for public consumption. Because the public loves the images, and I don't blame them. It's like, it's the extension of our visual senses. It's what allows us this sense of physical immersion in a system like Saturn. So I took that part of the job very seriously, made sure that the images were processed beautifully, paid as close attention as is possible in these circumstances to getting it to be natural color. It's not something the Voyager imaging team paid a lot of attention to because processing images for the public wasn't on their brain at that time. But you know, I made that something I wanted to do, and the public liked it. It worked, you know. But that part of it was like running a news magazine, like a weekly news magazine. I had to put out 5 pictures with 5 captions Monday and release them Monday, Tuesday, Wednesday, Thursday, Friday, every week. Every week. Went on for years.
Describe the cameras, because as a former photojournalist, I think about how digital cameras only really became the industry standard in the early 2000s. So what kind of camera did you stick on this thing, and how did you process them there afterwards?
This camera in your cell phone has greater, at least certainly greater resolution than our cameras have. They're only 1 megapixel, you know, a CCD, 1,000 pixels on a side. And we built these cameras in 1990, and you know, they have to be what are called flight qualified. So the technology really probably goes back to the late 1980s. And it's basically a telescope with lots of spectral filters in it, so we can flip, you know, we have 2 filter wheels and we have lots of filters in them, and you know, from a distance we can turn the filter wheels so we get a choice of many different filters, all scientifically purposed. And at the focus is this CCD. And then there's 2 of them. One is the narrow angle one, which goes in for the high resolution view, and one is the wide angle if we want to make a picture that covers a lot of territory.
Right.
And that was a technique, if you will, a method for going about doing an imaging investigation that was tried on Voyager and worked like a charm, to have 2 different focal lengths. So, I mean, and that's just a start. There's so much more to a camera system. You know, the different modes you could collect data in. Are you going to sum some pixels on the chip? You know, so you reduce the amount of information you have to send down to the ground. Different ways to compress the data. Anyway, it was complicated.
Right. The Voyager missions famously sort of passed out of our solar system, and they have kind of an infinite mission quality to them. But Cassini didn't, and this is a thing that I think that NASA does with some of the craft. Explain a little bit about the fate of Cassini, how the mission ended, and that's...
Well, going back to what I said about the 3-pronged approach that was enunciated way back in 1958, Cassini was the second step. Voyager was reconnaissance at Saturn, and Cassini was the orbiter. So orbiters don't go anywhere. Once you put it in orbit, you're not going to get it out. I mean, for God's sakes, it's bad enough to try to launch something off the Earth. Launching something from Saturn would be just prohibitively energetic. So, and there was no need to do it. We either could have just left it in orbit, but we didn't do that because the fear was whenever, you know, next week, 10 million years from now, it might, you know, it might crash into one of the moons that we did not want to contaminate in any way because they turned out to be of great interest for studies of the origin of life, perhaps. So it was just thought we'd be conservative, we'd be safe, and we'll deliberately send Cassini into the atmosphere of Saturn to burn up. So that's what happened. Big dramatic ending. Yeah. You
were talking about orbiting, which is essentially what the rings are doing. Talk just a little bit about the rings around Saturn.
What are they?
Made up, but exactly.
They're just countless numbers of icy bodies, from the tiniest little bits of like talcum powder to ice boulders the size of houses, and everything in between. And they're in independent orbit around Saturn. And the whole system is what we call a very equilibrated system. It started out as a cloud of debris, probably, most likely, a pre-existing moon that got smashed up by an incoming projectile. We don't exactly know when this happened, but could have happened, well, anyway, there's that's a long story, but anyway, so it got busted up, and it spreads out. When you do this, it spreads out around the planet, but it tends to be puffy. I mean, it tends to be a thick kind of system of debris, orbiting debris. But over time, as these particles collide with one another, this is just freshman physics, they retain their angular momentum, but they lose energy. And the result of that is that they all collapse down into a disk, a very flat disk, so that they can be really moving very quickly in orbit. In the case of Saturn's rings, 20 to 40,000 miles per hour, but they only very gently jostle each other, maybe millimeters per second. So if you have the idea of cars speeding along a freeway like in LA, lots and lots and lots of cars going at high rates of speed, but relative to each other, they hardly move at all. That's not too bad an analogy.
How thick?
How thick? 30 feet thick. Yeah, I don't know how big the room is we're in now, but yeah, just like two stories in a modern day building.
Right.
Yeah.
So moving to the second part and getting to the human machine aspects of this. This is obviously a completely machine mediated exploration. Talk about how you get such beautiful images, how you get such evocative images that help you research a place that's so far away.
You mean from a machine?
Yes.
Well, okay, so let me just go back. Let me just talk about the whole machine thing. You would never, you'd be terribly foolish to send humans to a place whose environment you didn't understand. I love to point out to people, think about what it would have been like if we had sent astronauts to Mars before we knew that every Martian spring the planet undergoes global dust storms that last for months, or at least weeks. That wouldn't be a good situation to put astronauts in. So it will always be that you precede the exploration of a body with robots. And we know how to do this now. We have become experts at doing this. The kinds of things we've been able to do with robotic planetary spacecraft is just remarkable. And certainly for the outer solar system, we'll be doing that for a very long time, because there's no need. Right now there's no need. We're not at the stage where it would be beneficial to send humans to a place like Saturn or one of its moons.
Right.
It's not even clear we're there yet with Mars, and we've sent a lot of spacecraft to Mars, because we just have been able to do so much with those with robots. So it's working. I mean, at some point in time, there may be a desire to do that. There may be some particular thing that is just so complex, requires a lot of intelligence on the ground, and the ability to recognize things quickly. Or maybe it'll just be that we send people there to learn how to live in such an environment. I suppose eventually we'll have outposts throughout the solar system. I'm not one to be thinking that we're going to take humans on the Earth and move them to a place like Mars. Okay, we have 7 billion people on the Earth, and there's no room for all of them on Mars. So, and there would be no need to do that. It'll be more like the way we inhabit Antarctica. Antarctica has a continuously inhabited scientific outpost. Okay, it's not the same people, they come and they go, right? But there's always someone there, and they're doing scientific, they're doing science, astronomical observing, gathering fallen meteorites on the ice fields and so on. And I suspect that that's what we'll do when humans make it out into the solar system. And maybe even it'll be extreme vacations, But to really live, if we had the wherewithal to go live on a place, let's say like Titan, which is a moon of Saturn, I think we should take those capabilities and make sure that our home planet is still suited for us.
Right. Well, when a lot of us think about robots doing exploring, whether it's underwater or in a tough environment, the distance between the human and the robot is so close. And so I think part of the fascination is how do you control something that's so far away? How long does it take the signal to get there? Talk a little bit about that.
Okay, so you get used to the light travel time. It takes, for Saturn, it takes about an hour and a half, an hour and 20 minutes for a signal to get there and a signal to get back. And it's a spacecraft that knows how to be autonomous. Okay. Voyager was too. Voyager was the first autonomous spacecraft, but they really refined it to an art with Cassini. And
so if you want to take a picture, obviously snapping the picture at the right time is a matter of knowing where the craft is going to be and sending the signal at the right time. So
you have to know what we call the predict trajectory. You have to know where the spacecraft is going to be at the time you want to take the picture. Not only the spacecraft, you got to know where all the bodies are in the Saturn system. Right. And you got to know where the sun is. And you want to know where other celestial objects are. The people who navigate, they navigate by looking at the position of stars relative to the spacecraft. So it's like we have to know exactly where everything is. I mean, if I want to, take my cameras and turn it enough so I take a picture of Mimas, I got to know where Mimas is. And so we acquired a lot of information regarding moons, for example, their orbits and so on from Voyager. And then there are observations made from ground-based telescopes that help us in that regard. You can just put all this data together and solve the proper equations and come out with what are called the orbital elements that tell you where things are going to be. And the same goes for Saturn, the orbit of Saturn around the sun, because that helps you figure out where the sun is once you're at Saturn yourself, and so on. And so, and then of course as the mission went on, and we were always taking pictures of moons for the purpose of refining orbits. That was in fact one of our scientific objectives, was to ask the question, are the orbits changing? But as the mission went on, we knew those orbits down to a gnat's eyebrow. I mean, it was great. So whenever we take a picture of something, if we wanted to get it in the center of the frame, by golly, it was in the center of the frame. Right. Yeah, it was cool.
And so you took some pretty famous pictures in this way, famously straight onto the rings to see their depth. And another one, I can't recall the name of it.
Well, are you talking about our glorious pictures of Earth?
Yes.
Yes, of course. Yeah, we have the first one, which was September '06. We were very far away reasonably far away from Saturn, so we got a big global view. And we deliberately put the spacecraft into a position where it was in the shadow of Saturn, because then you can look. Well, I'll just say that's a geometry that allows you to do things scientifically you couldn't otherwise, to get the sun out of the way and not shining on the optics of your camera. And we caught the Earth in that picture. That was the first one, and that was I think our most popular picture at the time. And then later on, I did what I ended up calling the day the Earth smiled, was do a picture like that again. It was really a way to do the pale blue dot picture all over again, except this time invite the public out to participate. And I'll talk about that too during the talk tonight.
Very good, very good. Do we have any questions from our online audience or from our audience here today?
So when you get the pictures, how do you interpret them? I know that you mentioned...
You're on.
Yeah.
I know that you mentioned putting them into a data processor, but do you use things like geomorphology or geography to kind of say, well, this is water and this is sand or dust? Or...
Okay. So I'll just explain the process, how the images get here. We take images on a CCD, and they become, when you do that, they become numbers. They become an array of numbers, the numbers being the brightness. If we take pictures through different filters, we have the filter in front of the detector, behind the telescope, but in front of the detector. If we took pictures, for example, in red, and then another one in green, and then another one in blue, we could composite them together. It would look like color to you. But they're numbers, and they get transmitted back to the Earth as on the back of a constant frequency signal. Well, okay, so just on what's called the telemetry signal, just electromagnetic radiation of a certain wavelength, and we perturb it in such a way so that the way it's slightly different from the wavelength or the frequency or whatever parameter it is we're encoding, that tells us what that number is. So we're receiving at the Deep Space Network, there's 3 stations all over the world, Parkes in Japan, Goldstone in California, and Australia. Parkes in Australia, I forget. Madrid, there's one in Madrid. They're like every 120 degrees, so there's always an antenna underneath the spacecraft, and they collect the information. Those data, those bits of information, get relayed then to the Jet Propulsion Laboratory, and the Jet Propulsion Laboratory strips out the signals, let's say, that are the images, our images. Every instrument is doing this too in their own way, but ours gets reconstructed into a 2-dimensional image. And then they send those images along with metadata that the spacecraft is collecting while the images are being taken. They transmit that to us in, well, actually, they send that to us in, my operations center is in Boulder, Colorado. And then we intercept that. And I didn't mean that the images go through a data processor to extract scientific information. It's more things like, what is the viewing geometry? You know, where is the sun relative to the target we just imaged? How high, for example, how high above the rings, when we're looking at the rings, how high above the rings was the spacecraft when it took that picture? Because those are the kind of geometrical information that you need if you want to go and then do something like figure out, you know, we're seeing a patch of ice on this moon or a patch of something on this moon. At what latitude and longitude is it? Well, you can't figure out what the longitude and latitude system on this moon even is unless you have all that other geometrical information. So that's essentially what happens.
We have a question online. Siddiq would like to know more about Saturn's rings. You've already mentioned that they're mostly made out of ice, and that the largest one is about the size of a house. I found it really fascinating, absolutely fascinating, that the thickness of the rings, the thickness of the ring is only 30 feet. That's 10 meters, which, you know, we're used to in space. We're used to dealing in astronomical terms in terms of distance. Is there anything else you can tell us that would surprise people about the rings?
Okay, let's see.
Maybe some of the patterns that you found.
Yeah,
in the
but that's,
rings?
I'm trying to think which pattern. Okay, I'm trying to think what surprised us. Here's something that blew us away. I mean, really, like, it was what? We found, okay, so you can get waves in the rings in 2 ways, okay? You could get a wave in the ring that is really, when you look at it, it looks like a wave pattern. But really what it is the material has in some locations been compressed together, so it looks brighter if you're looking in reflected light. And then right next to it, there's fewer particles there because it's more rarefied, and then it looks darker. And right next door, it looks compressed, and next door to that, it looks rarefied. And if you look at it, you know, as a picture, it looks like you've got stripes on your picture. Looks like a wave, okay? You can also get a wave that's more like the traditional wave you think of when you think of waves, where the whole ring plane is actually warped. And if it looks like a pattern, like bright, dark, it's usually because of the way this corrugation is reflecting the sunlight. It's bright on one side, maybe it's shadowed on the other, bright on one side, shadowed on the other. Okay, so we found a wave pattern okay, let me back up. We were there when southern autumnal, well, northern vernal equinox happened. This was the sun seen from Saturn. The sun moved from the southern hemisphere to the northern hemisphere, which meant for a short period of time, it was hovering right above the equator of Saturn, which means it was hovering right edge onto the rings. Well, this was the best possible circumstance in which to see shadows that were created by things that were protruding out of the rings. And it's not something we ever can see from the Earth. And of course, from the Earth, you don't get the kind of resolution, kind of detail we have when you're there on top of the planet. So we took great advantage of this and took lots of pictures during this equinox period. And these shadows, I forget actually when they started to appear, but maybe a year. Maybe it was a year before the actual equinox happened that we started to see shadows. But we saw around the equinox period a very subtle wave pattern. And we worked out, this was one of the people who worked on my team, worked out how high the ring plane had to be in order to produce what we were seeing. And it was just meters. I mean, in some places the ring is actually warped and it's a kilometer kind of a warp, but this was only several meters. It was very subtle. And not only that, but it was something that looked like it was winding up and getting tighter and tighter. And, you know, very puzzling, didn't know what was causing it. And finally, they worked out that it was caused by the impact of probably a comet, maybe a string of comets, into the rings that immediately put some segment of the ring particles on inclined orbits. And this eventually, through the interactions that the particles have with each other, we call it self-gravity. You know, one particle actually is affecting the particles around it through its gravity. This ended up being a ripple that eventually spread across the rings. So we were seeing the effect of impact, and they worked out. These people on my team, they were not even official, they were people we added later, young scientists on our team, worked out that this thing was wound up. Well, they unwound it to see, well, when did it actually start? When did this happen? And they worked out that it happened, I forget, don't quote me on the year, but it happened in mid-1983, something like that. It was just wild that we were seeing the effects of an event that happened only, a couple of decades ago. So that just really, really surprised us. It suddenly just opened up a whole new way of looking at the rings, that they're recording things in the modern era, and that they actually could record an impact. It was just not something we anticipated at all. And another thing that surprised us was the fact that at ring edges, certain ring edges, the ring, now mind you, this is a sheet of debris 30 feet thick, but at ring edges, the material was protruding miles above the ring, 2 miles above the ring in 2 cases. And I mean, we did expect there would be some vertical dimension to the rings. I mean, we've known that for a long time. There should be some, but we weren't thinking miles, we're thinking meters. And this was wilder than we could imagine. I mean, imagine mountainous piles of rubble, So those were 2 tremendously surprising things.
Where in relation to the rings was Cassini most of the time? Was it outside the rings?
Oh,
orbiting?
always outside the rings, except for the very, very final 20 orbits when we put it between the planet and the innermost ring, and it orbited there. And we didn't dare do that ever because we thought that's death. There's certainly some scattered ring material there, and the spacecraft will just collide with it and die. We never would ever put spacecraft in a gap in a ring like that, but we thought it was the end of the mission, and there was good reason to do it because it makes you come very close to the planet, and that allows you to get another dimension, if you will, on the interior structure, the gravitational field, which from that you could read the interior structure. Well, it turned out we put the last 20 orbits were these very close orbits to the planet inside the inner ring, and orbit after orbit, nothing happened. It just kept going, orbit after orbit. It lived through all 20 orbits. It means that that space is practically empty, and we didn't realize how empty it was. And so it worked out beautifully because we found out something about the interior structure of Saturn that we weren't sure of before, and that is that it's called rotation on cylinders. It's a little bit complicated, but there was two choices. It either, I don't know how to even describe this, but there were two choices about what the interior structure of Saturn might be like, and couldn't really decide which was which, and this last set of orbits allowed us to nail it. So it was a great success right till the end, right till the very end.
It almost seems improbable that over the years that this thing was flying, that it never sort of got knocked into by something. Did that ever happen during the mission?
Nothing ever went wrong. We all say that. It could have been human error. It could have been what we call fall off the tour. The tour is the trajectory that we plan. And it always followed the trajectory that we planned. No one accidentally sent the wrong number and sent it off in the wrong direction, in which case we'd have to scramble and replan all our observations that followed. That would have been a nightmare. That never happened. Nothing, the spacecraft never had any problems. It was just working like a charm, except that it was arthritic. The reaction wheels that we used to turn the spacecraft, that was one way to turn the spacecraft, use these things that are basically like gyroscopes. But again, it's kind of complicated, I won't go into it, but they constantly move, they constantly spin, and they got arthritic after a while. They didn't spin so well after a while, but it's still, the engineers figured out how to deal with all that. So we were just blessed that nothing ever went wrong.
One of the scientists on the mission was quoted as saying that you end up feeling as one with the craft.
Yes.
You never said that Cassini went and did this. We flew in to this area.
Is that what I'm saying?
No, but I mean, is that how it felt to you as well?
Yeah. Oh, yeah. Of course. Especially, you can imagine the engineers who are operating this thing and caring for it all this time. I mean, really, they're hovering over it, so to speak, and making sure all its systems are working well, and you can imagine how they feel about it. The scientists are off, we collect our data, and we were happy as a clam, and they're still there, making sure it's doing what it's supposed to do. So they really feel a connection to it.
Right.
Yeah.
Were you there for the event at the end of Cassini's mission?
Oh yeah, I was. Yes, of course I was.
Describe the atmosphere in that event.
Well, it was just, I was at the California Institute of Technology. They'd set up these big screens on their big mall area, this big grassy area, and they had set up chairs to look at the screen, and it was a big deal. It was really a big deal. There was a lot of people there all looking at the screens, and the thing that we were all there to see was just the signal. It's just a signal that was there, and then it started to decrease, and then suddenly it wasn't there anymore. And we knew that was when it just disintegrated. It started to lose its orientation, so the high gain antenna was no longer pointing towards the Earth and giving us the signal. And the engineers had worked this out so well that they knew once the signal was lost, how much longer it would be before the spacecraft would be completely disintegrated. So, we knew when it ended. But another thing that's amazing to me is that they knew that spacecraft and how to operate it so well, and we knew, by the end of the mission, we knew the structure of the Saturnian atmosphere so well that they predicted to within 30 seconds when the thing was going to die. I mean, that's another thing that blew me away. To within 30 seconds. It's remarkable.
Very remarkable. Well, thank you so much for speaking with us.
Oh, it's my pleasure.
We really
my pleasure.
appreciate
It gives
it.
me the chance to just remember how great it all was. Yeah.
And thank you to our online audience as well. Carolyn will be speaking also live on Facebook at 5:30, so make sure and come back and join us for that. And thank you for being here with us for this special conversation.